Imagine a cosmic roll of the dice, a mathematical journey that could lead us to our galactic neighbors or leave us alone in the vast, silent expanse of space. This isn't a game of chance, but a serious scientific endeavor encapsulated in what's known as the Drake equation. It's our best shot at estimating the number of communicative, intelligent civilizations in our Milky Way galaxy. But here's the catch. The answer isn't straightforward. It's a complex puzzle filled with variables that spark debates, inspire optimism, and fuel skepticism. Stick around, because we're about to dive into the fascinating world of the Drake equation, breaking down its components, exploring the assumptions, and weighing in on the great alien life debate. Who knows? By the end, you might just find yourself looking at the stars a little differently. The Drake equation, an overview. The Drake equation, formulated by astronomer Frank Drake in 1961, is a probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. It's a straightforward yet profound formula. N equals our asterisk, FP, NE, FL, Phi, FCL. Here, N represents the number of civilizations with detectable electromagnetic emissions. The variables are asterisk, FP, NE, FL, Phi, FC, and L stand for the rate of star formation, the fraction of stars with planets, the number of planets per star capable of supporting life, the fraction of planets where life actually develops, the fraction of life-bearing planets where intelligent life emerges, the fraction of civilizations that develop detectable technologies, and the length of time such civilizations release detectable signals, respectively. Each variable in the Drake equation is a topic of intense debate and speculation. For instance, our asterisk, the rate of star formation, is relatively well understood thanks to astronomical observations. However, variables like FL, the fraction of planets where life develops, and Phi, the fraction where intelligent life emerges, are highly speculative. These variables hinge on our understanding of abiogenesis, the process by which life arises naturally from non-living matter, and the conditions that foster the evolution of intelligence. Skeptics argue that life, especially intelligent life, might be an exceedingly rare phenomenon, given the stringent conditions it requires. Optimists, on the other hand, point to the robustness of life on Earth, thriving in extreme environments, suggesting that life might be more common than we think. The assumptions underlying the Drake equation are as contentious as the variables themselves. One key assumption is that life on Earth is a typical example of life elsewhere. This is known as the mediocrity principle, which suggests that Earth is not unique and that the conditions found here are common throughout the universe. However, this assumption is challenged by the rare Earth hypothesis, which posits that the emergence of intelligent life on Earth may be an improbable and singular event due to a confluence of highly unlikely circumstances. Another assumption is that civilizations release detectable signals into space for a significant period. This is debatable, given that human civilization has only been broadcasting radio waves for about a century, a blink of an eye in cosmic terms. The Drake equation has sparked a spectrum of views, from the optimistic to the skeptical. Optimists, like astronomer Carl Sagan, have argued for high values of the equation's variables, leading to estimates of thousands of communicative civilizations in our galaxy. They point to the vast number of exoplanets discovered in recent years, many in the habitable zone of their stars, as evidence that life could be widespread. Skeptics, however, argue for lower values, with some even suggesting that we might be alone in the Milky Way. They highlight the lack of empirical evidence for extraterrestrial life and the numerous filters that life must pass through to emerge and evolve. Despite these debates, the Drake equation remains a powerful tool for stimulating scientific discussion and guiding the search for extraterrestrial intelligence. Historical context and development. The Drake equation emerged from a time when humanity was just beginning to gaze beyond its own planet with serious intent. The Cold War era sparked a surge in scientific exploration, with space becoming the final frontier. It was against this backdrop that astronomer Frank Drake sought to estimate the number of communicative, intelligent civilizations in our Milky Way galaxy. He introduced the equation at a meeting in Green Bank, West Virginia, aiming to stimulate scientific dialogue about the search for extraterrestrial intelligence, said he. The equation was never meant to provide a definitive answer, but rather to frame the discussion and identify key areas of uncertainty. At its core, the Drake equation is a probabilistic argument. It combines factors like the average rate of star formation, the fraction of stars with planets, the number of planets that could support life, and the likelihood of life actually emerging. Then it narrows down further to consider the chances of intelligent life developing and the likelihood of that life being technologically advanced enough to communicate. Each variable represents a complex interplay of astrophysical, biological, and sociological factors. For instance, the variable representing the fraction of planets where life develops is influenced by everything from planetary chemistry to the stability of the planet's environment. The equation's power lies in its ability to break down a vast, uncertain problem into manageable parts. Debates surrounding the Drake equation often hinge on the assumptions made for each variable. Optimists argue that life is likely to be abundant, pointing to the rapid emergence of life on Earth and the discovery of extremophiles, organisms thriving in extreme environments. They suggest that even if the chances for each step are low, the sheer number of stars and planets in the galaxy makes the existence of extraterrestrial life probable. Skeptics, however, emphasize the lack of empirical evidence and the many steps where life could fail to emerge or evolve. They highlight the rarity of Earth-like planets and the unique conditions that allowed life to flourish here. The equation's flexibility allows for a wide range of estimates, from a galaxy teeming with life to one where Earth is a rare anomaly. The Drake equation has evolved alongside our understanding of the universe. Initially, many variables were pure speculation. Today, missions like Kepler and the ongoing work of the James Webb Space Telescope provide data on exoplanets, refining our estimates for variables like the number of stars with planets. Yet, questions about the likelihood of life and intelligence remain deeply uncertain. The equation serves as a reminder of how much we still don't know. It's a tool for structuring our ignorance, guiding research, and sparking imagination. Whether the answer is optimistic or skeptical, the Drake equation continues to be a cornerstone in the ongoing quest to understand our place in the cosmos. Understanding the variables. The Drake equation, formulated by astronomer Frank Drake, is a probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. At its core, the equation is a product of several variables, each representing a different factor in the development of such civilizations. Understanding these variables is crucial for grasping the equation's implications and the ongoing debates surrounding it. The first variable, ****, represents the average rate of star formation in our galaxy. This is relatively straightforward, as astronomers have a good grasp on the number of new stars being born each year. However, things get more complicated with the next variable, \F_P_, which denotes the fraction of those stars that have planetary systems. While it's now widely accepted that planetary systems are common, the exact fraction is still a topic of debate. Optimists might argue that every star has at least one planet, while skeptics might point to the need for more data to confirm this. The third variable, \N_E_, is the average number of planets that could potentially support life per star that has planets. This is where things get even more contentious. Some argue that Earth-like planets are rare, given the specific conditions needed for life as we know it. Others, however, highlight the discovery of exoplanets in the habitable zone of their stars, suggesting that such planets might be more common than previously thought. The next variable, \F_L_, represents the fraction of those planets where life actually develops. This is highly speculative, as we only have one data point, Earth. Optimists might point to the resilience and adaptability of life on our planet, while skeptics might argue that the conditions on Earth are exceptionally fortunate. The following variable, \F_I_, is the fraction of life-bearing planets where intelligent life evolves. This is perhaps the most debated variable, as it touches on the nature of evolution and the uniqueness of intelligent life on Earth. Some argue that intelligence is a likely outcome of evolution, given its adaptive advantages. Others, however, point to the lack of evidence for intelligent life elsewhere in our solar system, suggesting that it might be exceedingly rare. The next variable, f_c_, represents the fraction of intelligent civilizations that develop technology to communicate with others. This is also contentious, as it depends on a variety of cultural, technological, and environmental factors. Finally, \L is the average length of time such civilizations release detectable signals into space. This variable is highly uncertain, as it depends on the longevity of civilizations and their willingness or ability to communicate. Optimists might hope that civilizations last for hundreds of thousands or even millions of years, while skeptics might argue that civilizations are likely to destroy themselves relatively quickly, given the challenges they face. Each of these variables is interconnected, and changes in one can significantly impact the overall estimate of the number of communicative extraterrestrial civilizations in our galaxy. Variable 1. The rate of star formation. Stars are the building blocks of galaxies, and their formation rate is a critical factor in understanding the potential for life in the universe. The rate of star formation is typically measured in solar masses per year, with the Milky Way galaxy currently forming stars at a rate of about 13 solar masses per year. This rate, however, has not been constant throughout the galaxy's history. In the past, star formation was more rapid, with peaks occurring billions of years ago. Understanding this variable is crucial because stars provide the necessary energy and elements for planetary systems to form and potentially support life. The Drake equation uses this variable, denoted as our asterisk, to estimate the number of communicative extraterrestrial civilizations in the Milky Way. Optimists argue that a high rate of star formation increases the likelihood of habitable planets. More stars mean more opportunities for planetary systems to form, and with them, the potential for life. They point to the sheer scale of the universe, with hundreds of billions of galaxies, each containing hundreds of billions of stars. Even if only a tiny fraction of these stars have planets capable of supporting life, the numbers could still be enormous. This perspective encourages the belief that we are not alone and that the universe is teeming with life. Skeptics, on the other hand, highlight the uncertainties and variability in star formation rates. They argue that while the rate may be high, many stars may not be suitable for life. For instance, massive stars burn out quickly, leaving little time for life to develop. Additionally, stars with high metallicity, a measure of elements heavier than hydrogen and helium, are more likely to have planetary systems, but not all stars meet this criterion. Furthermore, the initial burst of star formation in the early universe may have produced stars with different properties, making them less likely to host life as we know it. These factors temper optimism and suggest that the actual number of life-supporting planets might be lower than hoped. Debates also surround the assumptions underlying the rate of star formation. One key assumption is that the rate is relatively constant over time, which may not hold true. Another is that star formation leads to the formation of planetary systems capable of supporting life. This is not guaranteed, as many factors influence a planet's habitability. Additionally, the equation assumes that life will develop given the right conditions, a hypothesis that remains unproven. These assumptions highlight the speculative nature of the Drake equation and the need for more data to refine our understanding of the universe and our place within it. Variable 2. The fraction of stars with planets. The Drake equation, a probabilistic argument to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way, hinges on several variables. Among these, the second variable, denoted as \N_E_, represents the fraction of stars with planets. This variable is pivotal, as it sets the stage for the possibility of life beyond Earth. Initially, this fraction was a matter of speculation, as the first confirmed detection of an exoplanet, a planet orbiting a star outside our solar system, occurred in 1992. Since then, our understanding has evolved dramatically, thanks to missions like NASA's Kepler Space Telescope, which has identified thousands of exoplanets. The discovery of exoplanets has reshaped our perspective on \N_E_. Early estimates were cautious, with some scientists suggesting that only a small percentage of stars might host planets. However, the data now suggests that planet formation is a common byproduct of star formation. In fact, it's now widely accepted that nearly every star in the Milky Way has at least one planet orbiting it. This optimism is fueled by the diversity of planetary systems observed, ranging from hot Jupiters orbiting close to their stars to Earth-sized planets within the habitable zone, where liquid water could potentially exist. The Kepler mission alone has identified over 40 exoplanet candidates, with many stars hosting multiple planets. Despite this optimism, skepticism persists. One point of debate is the fraction of these planets that are truly habitable. While many exoplanets have been discovered, only a small subset reside within the habitable zone of their stars. Additionally, the presence of a planet in the habitable zone doesn't guarantee it's habitable. Factors like atmospheric composition, geological activity, and the presence of liquid water are crucial. For instance, Mars is within our solar system's habitable zone, but it lacks a substantial atmosphere and liquid water on its surface, making it inhospitable to life as we know it. Furthermore, the stability of planetary systems over geological timescales is another consideration. Some planetary systems may be dynamically unstable, leading to collisions or ejections that could render them uninhabitable. The assumptions underlying \n_e_ are continually being refined as our observational capabilities improve. The transition from speculation to empirical evidence has been profound. What was once a variable filled with uncertainty is now grounded in a growing body of data. However, the debate continues, with optimists pointing to the high frequency of planet formation and skeptics emphasizing the stringent requirements for habitability. This ongoing dialogue is a testament to the dynamic nature of scientific inquiry, where each new discovery reshapes our understanding of the cosmos and our place within it. Variable 3. The number of planets per star capable of supporting life. The Drake equation, a probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way, hinges on several variables. Among these, variable 3, often denoted as \n_e_, represents the average number of planets per star capable of supporting life. This variable is pivotal as it directly impacts the overall estimate of potential habitable worlds. Assumptions about \n_e_ vary widely. Optimists might point to the sheer number of exoplanets discovered, suggesting that a significant fraction could be habitable. For instance, data from the Kepler mission indicates that nearly every star hosts at least one planet, and a portion of these planets reside in the habitable zone, where conditions might allow for liquid water to exist. Skeptics, however, argue that habitability depends on a myriad of factors beyond just location. Atmospheric composition, magnetic field strength, and geological activity all play crucial roles. Mars, for example, lies within the Sun's habitable zone but lacks a substantial atmosphere and active geology, making it inhospitable for life as we know it. Debates surrounding \n_e_ often center on the definition of habitable. Some scientists adopt a broad definition, considering any planet with the potential for liquid water to be habitable. Others take a more conservative approach, requiring additional conditions like a stable climate and the presence of essential elements for life. This discrepancy leads to a wide range of estimates. Optimistic views might suggest that up to 20% of stars could have habitable planets, while more skeptical perspectives might place that number closer to 1%. The discovery of exoplanets has significantly influenced discussions about \n_e_. Systems like TRAPPIST-1, which hosts 7 Earth-sized planets with 3 in the habitable zone, fuel optimism. However, the actual habitability of these planets remains uncertain. Factors like tidal locking, where one side of the planet perpetually faces the star, could render some worlds inhospitable despite their location. Additionally, the presence of a thick atmosphere or extreme geological activity might make others unsuitable. These complexities highlight the challenges in accurately estimating \n_e_. In summary, the number of planets per star capable of supporting life is a contentious and multifaceted variable. It encompasses a range of scientific, philosophical, and methodological debates. While the discovery of exoplanets has provided valuable data, the true extent of habitability remains an open question. As our understanding of planetary systems and the conditions necessary for life continues to evolve, so too will our estimates of \n_e\. This variable serves as a reminder of the intricate and interdependent factors that contribute to the potential for life beyond Earth. Variable 4, the fraction of planets where life actually develops. The Drake equation, a probabilistic approach to estimate the number of communicative extraterrestrial civilizations in the Milky Way, hinges on several variables. Among these, variable 4, often denoted as \f_l_, represents the fraction of planets where life actually develops. This variable is particularly contentious, as it grapples with the fundamental question of how easily life emerges given the right conditions. Optimists argue that life is a cosmic imperative, pointing to the rapid emergence of life on Earth shortly after the planet became habitable. The discovery of extremophiles, organisms thriving in extreme environments, further fuels this perspective. These hardy life forms suggest that life can take hold in a wide range of conditions, not just the temperate, Earth-like environments once thought necessary. Proponents of this view often cite the principle of mediocrity, which posits that Earth is not uniquely suited for life, but rather an average planet. If this is true, then life should be relatively common throughout the universe. Skeptics, however, contend that the emergence of life is a rare and complex process. They highlight the numerous steps required for life to arise, from the formation of essential organic molecules to the development of self-replicating systems. The transition from simple organic compounds to the first living cells is still not fully understood, and some scientists argue that this transition might be extraordinarily unlikely. Additionally, the fossil record shows that while life on Earth appeared relatively quickly, the transition to complex, multicellular life took billions of years. This long timescale suggests that even if life starts easily, evolving into complex forms might be a bottleneck. The debate over \f_l_ is further complicated by the lack of empirical data. With only one example of life, Earth, scientists have limited information to work with. The discovery of exoplanets in the habitable zones of their stars has provided some hope for testing these theories, but direct evidence of life beyond Earth remains elusive. Until such evidence is found, the value of \f_l_ will remain speculative, shaped by philosophical assumptions as much as scientific data. This uncertainty underscores the importance of continued exploration and research, as each new discovery could significantly alter our understanding of life's prevalence in the universe. Variable 5, the fraction of planets where life evolves into intelligent beings. The Drake equation, a probabilistic approach to estimate the number of communicative extraterrestrial civilizations in the Milky Way, comprises 7 variables. Among these, variable 5, denoted as \f_i_, represents the fraction of planets where life evolves into intelligent beings. This variable is particularly contentious, as it hinges on our understanding of evolutionary biology, planetary conditions, and the definition of intelligence itself. Optimists argue that the emergence of intelligent life is a near-inevitable consequence of evolution given sufficient time and favorable conditions. They point to the rapid ascent of humans on Earth, where complex life forms emerged relatively quickly in geological terms. Proponents of this view often cite the principle of mediocrity, suggesting that Earth is not uniquely privileged and that intelligent life should be common elsewhere. They also highlight the diversity of life on Earth, from bacteria to primates, as evidence that evolution tends toward increased complexity and intelligence. However, this perspective is not without its critics, who question whether human intelligence is a typical outcome or a rare fluke. Skeptics, on the other hand, contend that the evolution of intelligent life is an extraordinarily rare event, contingent on a confluence of highly improbable factors. They emphasize the role of chance and contingency in evolution, as illustrated by the theory of punctuated equilibrium, which posits that evolution proceeds in fits and starts rather than a steady march toward complexity. For instance, the development of human-like intelligence required the convergence of numerous factors, including bipedalism, tool use, and complex social structures. Additionally, skeptics point to the Fermi Paradox, which questions why, if intelligent life is common, we have not yet detected any signs of it. This paradox suggests that the path to intelligence might be far more arduous and rare than optimists believe. The debate surrounding _f_I_ is further complicated by the lack of empirical data. Without examples of extraterrestrial life, scientists must rely on theoretical models and analogies drawn from Earth's biosphere. Some researchers focus on the concept of the Great Filter, which posits that there is a step in the evolution of life that is extremely difficult to surpass. This filter could be behind us, such as the transition from single-celled to multi-celled organisms, or it could lie ahead, like the development of interstellar travel. If the Great Filter is ahead of us, the fraction of planets where life evolves into intelligent beings could be vanishingly small. Conversely, if we have already passed the Great Filter, intelligent life might be more common than we think. This uncertainty underscores the need for continued exploration and research, both within our solar system and beyond. Variable 6. The fraction of intelligent civilizations that develop detectable technologies. The Drake equation, a probabilistic framework for estimating the number of active, communicative extraterrestrial civilizations in the Milky Way, includes a variable often overlooked but crucial to its outcome: the fraction of intelligent civilizations that develop detectable technologies. This variable, typically denoted as a simple fraction, encapsulates a complex interplay of cultural, technological, and environmental factors. It's a measure of how likely it is that an intelligent species, once it evolves, will develop technology advanced enough to be noticed by others, like us, across the vastness of space. Optimists argue that the development of detectable technology is almost inevitable for any intelligent civilization. They point to the rapid technological progress seen on Earth, from the invention of the wheel to the launch of satellites, as evidence that intelligence and technology are intrinsically linked. They suggest that any civilization with the intelligence to develop tools and language will eventually create technology that leaks detectable signals into space, such as radio or television broadcasts. This perspective assumes that the path of technological progress is linear and that any intelligent species will follow a trajectory similar to ours. However, this view has been criticized for its anthropocentrism, as it projects human experiences onto entirely alien civilizations. Skeptics, on the other hand, contend that the fraction is likely to be very low. They argue that the development of detectable technology is not a guaranteed outcome of intelligence. For instance, a civilization might prioritize internal harmony and sustainability over technological expansion, leading to a different kind of progress that doesn't involve broadcasting signals into space. Alternatively, a civilization might develop technology but choose not to use it in a detectable way, perhaps due to an understanding of the potential risks. This perspective is supported by the Fermi Paradox, which questions why, if intelligent life is common, we haven't detected any signs of it yet. It also considers the possibility of the Great Filter, a hypothetical barrier that prevents civilizations from reaching detectable stages of technological development. The debate surrounding this variable is further complicated by the lack of empirical data. Without any confirmed examples of extraterrestrial intelligence, we can only speculate about the likelihood of detectable technology development. Some scientists suggest that we might be on the cusp of answering this question, as projects like the Search for Extraterrestrial Intelligence, SETI, and the Breakthrough Listen initiative continue to scan the skies for signals. Others argue that we might never find an answer, and that the Drake equation is more valuable as a tool for stimulating discussion and research than as a means of arriving at a definitive number. Regardless, the fraction of intelligent civilizations that develop detectable technologies remains a fascinating and contentious aspect of the ongoing search for extraterrestrial life. Variable 7. The length of time such civilizations release detectable signals. The Drake equation, a probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way, includes several variables that spark debate and speculation. Among these, variable 7, often denoted as L, represents the length of time such civilizations release detectable signals into space. This variable is particularly contentious, as it hinges on the lifespan of technologically advanced societies and their propensity for communication. Optimists argue that L could be quite large, pointing to humanity's own technological advancements. Since the mid-20th century, we've been broadcasting radio and television signals into space, which means L for Earth is at least several decades. Some suggest that advanced civilizations might develop even more long-lasting communication methods, such as laser-based systems or other forms of electromagnetic radiation. If these civilizations are stable and long-lived, L could span thousands or even millions of years. This perspective assumes that technological societies can avoid self-destruction and maintain the ability and desire to communicate across vast timescales. Skeptics, however, contend that L might be relatively short. They highlight the numerous existential risks that civilizations face, including nuclear war, climate change, artificial intelligence gone awry, or other unforeseen catastrophes. If these risks are common, the average lifespan of a communicating civilization could be brief. Additionally, some argue that advanced civilizations might choose to limit their signal emissions, either to avoid detection by potential threats or to transition to more secure forms of communication. In this view, L could be as short as a few centuries, drastically reducing the number of civilizations we might expect to detect. The debate surrounding L is further complicated by the lack of empirical data. Without any confirmed examples of extraterrestrial civilizations, we can only speculate based on our own experiences and assumptions. Some researchers propose that L could follow a distribution, with a few civilizations lasting for millions of years and many others being short-lived. This uncertainty makes L one of the most challenging variables to constrain in the Drake equation. Despite these challenges, exploring the possibilities and implications of different L values helps us refine our understanding of the cosmos and our place within it. Assumptions and limitations. The Drake equation, formulated by astronomer Frank Drake, is a probabilistic approach to estimate the number of communicative, intelligent civilizations in our Milky Way galaxy. It's a product of 7 variables, each representing a different aspect of the problem. These variables include the average rate of star formation, the fraction of stars with planetary systems, the number of planets per system that could support life, the fraction of suitable planets where life actually develops, the fraction of life-bearing planets where intelligent life emerges, the fraction of intelligent civilizations that develop detectable technologies, and the length of time such civilizations release detectable signals. Each of these variables is a source of assumptions and limitations, sparking debates among scientists. The first few variables, dealing with star formation and planetary systems, are relatively well understood thanks to modern astronomy. However, the equation quickly ventures into more speculative territory. For instance, the fraction of suitable planets where life develops is a contentious point. Optimists argue that life is likely to emerge given the right conditions, pointing to extremophiles on Earth that thrive in extreme environments. Skeptics, however, highlight the lack of empirical evidence for life elsewhere in the universe, suggesting that abiogenesis might be an extremely rare or even a once-off event. The debate intensifies with the variables related to intelligent life. Some scientists, like those involved in the rare Earth hypothesis, argue that the emergence of intelligent life requires an improbable confluence of astrophysical and geological events, making it exceedingly rare. They point to the fact that, despite the vast number of stars and planets, we have no confirmed evidence of intelligent extraterrestrial life. On the other hand, optimists like those in the SETI search for extraterrestrial intelligence. Community contend that intelligent life could be common, given the sheer number of potentially habitable planets. They also argue that the lack of evidence isn't evidence of absence, but rather a limitation of our current technology and observational capabilities. Moreover, the Drake equation assumes that intelligent civilizations are long-lived and technologically advanced enough to communicate across interstellar distances. This is another point of contention. Some scientists, like those advocating the Great Filter hypothesis, suggest that there might be a barrier that prevents civilizations from becoming advanced and long-lasting. This could be due to self-destruction, like nuclear war or climate change, or external factors, like asteroid impacts or gamma-ray bursts. Others argue that advanced civilizations might be so different from us that their communication methods are undetectable or incomprehensible to us. These assumptions and limitations highlight the speculative nature of the Drake equation, making it more of a thought experiment than a precise calculation. Yet, it remains a valuable tool for stimulating discussion and guiding research in the field of astrobiology. Probability theory basics. Probability theory is the mathematical framework that deals with the analysis of random phenomena. It provides the tools to quantify uncertainty and make predictions about events that may or may not occur. At its core, probability theory is concerned with the likelihood of different outcomes, given certain conditions. This is particularly relevant when discussing the Drake equation, which attempts to estimate the number of communicative extraterrestrial civilizations in the Milky Way galaxy. The equation is a product of several variables, each representing a different aspect of the problem. To understand the Drake equation, it's essential to grasp the basics of probability theory as it underpins the entire endeavor. The Drake equation is often written as n equals r asterisk, fp, ne, fl, phi, fc, l, where n represents the number of civilizations in the Milky Way galaxy whose electromagnetic emissions are detectable. The variables are asterisk, fp, ne, fl, phi, fc, and L stand for the rate of formation of stars suitable for the development of intelligent life, the fraction of those stars with planetary systems, the number of planets per solar system, with an environment suitable for life, the fraction of suitable planets on which life actually appears, the fraction of life-bearing planets on which intelligent life emerges, the fraction of civilizations that develop a technology that releases detectable signs of their existence into space, and the length of time such civilizations release detectable signals. Each of these variables is a source of debate and speculation, with optimistic and skeptical views shaping the estimates. Optimists tend to assign higher probabilities to each variable, leading to a higher estimated value for n. They argue that life is likely to be robust and adaptable, capable of arising in a wide range of environments. For instance, they might point to extremophiles on Earth, organisms that thrive in extreme conditions, as evidence that life can emerge and persist in seemingly inhospitable places. Skeptics, on the other hand, tend to assign lower probabilities, resulting in a lower estimated value for n. They might argue that the emergence of life requires an extraordinarily fine-tuned set of initial conditions, and that the transition from simple life to intelligent life is an extremely rare event. They could point to the fact that, despite extensive searching, no definitive evidence of extraterrestrial life has been found so far. The assumptions underlying each variable are a significant source of debate. For example, the variable FL, the fraction of suitable planets on which life actually appears, depends on assumptions about the ease of abiogenesis, the process by which life arises from non-living matter. Optimists might assume that abiogenesis is relatively easy and occurs frequently, while skeptics might assume that it is extremely difficult and rare. Similarly, the variable phi, the fraction of life-bearing planets on which intelligent life emerges, depends on assumptions about the likelihood of evolutionary processes leading to intelligence. Optimists might argue that intelligence is a likely outcome of evolution, given its adaptive advantages, while skeptics might argue that intelligence is a rare and contingent outcome, dependent on a specific and unlikely sequence of evolutionary events. These debates highlight the uncertainties and subjectivities involved in estimating the variables of the Drake equation. Bayesian probability and the Drake equation. The Drake equation, formulated by astronomer Frank Drake, is a probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. It's a product of several variables, each representing a different aspect of the likelihood of life emerging and evolving to the point of developing interstellar communication. Bayesian probability, a framework for updating beliefs in the light of new evidence, can be applied to the Drake equation to refine these estimates. The Drake equation is composed of 7 variables: the average rate of star formation, the fraction of those stars with planets, the number of planets per star that could potentially support life, the fraction of those planets where life actually develops, the fraction of life-bearing planets where intelligent life emerges, the fraction of intelligent civilizations that develop technology for interstellar communication, and the length of time such civilizations release detectable signals into space. Each of these variables is subject to debate and uncertainty. For instance, the rate of star formation is relatively well understood, but the fraction of life-bearing planets where intelligent life emerges is highly speculative. Bayesian probability allows us to incorporate new scientific findings and adjust our estimates accordingly. As new exoplanets are discovered and characterized, or as our understanding of abiogenesis, the process by which life arises naturally from non-living matter, improves, we can update our beliefs about these variables. Optimistic views of the Drake equation often emphasize the sheer size of the universe and the high probability of life emerging given the right conditions. They might point to the rapid development of life on Earth after the planet became habitable, suggesting that abiogenesis is relatively easy. Skeptical views, on the other hand, might highlight the numerous steps required for life to emerge and evolve into an intelligent, technological civilization, each with its own low probability. They might also point to the Fermi Paradox, which questions why, if intelligent life is common, we haven't observed any evidence of it. Bayesian probability allows us to weigh these different perspectives and incorporate new evidence as it becomes available. For example, the discovery of extremophiles, organisms that thrive in extreme environments, might increase our estimate of the fraction of life-bearing planets where life develops. Conversely, the rarity of complex, multicellular life on Earth might decrease our estimate of the fraction of life-bearing planets where intelligent life emerges. Debates surrounding the Drake equation often hinge on these assumptions. Some scientists argue that we should focus on the variables that are most amenable to empirical study, such as the fraction of stars with planets or the number of planets per star that could potentially support life. Others argue that we should also consider the possibility of non-terrestrial life forms, which might have entirely different requirements for habitability. Bayesian probability provides a flexible framework for incorporating these different perspectives and updating our estimates as new evidence comes to light. It allows us to acknowledge the uncertainty inherent in the Drake equation while still making reasoned estimates about the likelihood of intelligent life elsewhere in the universe. Ultimately, the Drake equation and Bayesian probability together provide a powerful tool for thinking about one of the most profound questions in science. Are we alone in the universe? Monte Carlo simulations. Monte Carlo simulations are a powerful tool used to explore the vast uncertainties embedded in the Drake equation, which estimates the number of communicative extraterrestrial civilizations in our galaxy. This statistical method involves running multiple simulations with different sets of input variables, allowing researchers to observe the range of possible outcomes. In the context of the Drake equation, these variables include the average rate of star formation, the fraction of stars with planets, the number of planets that could potentially support life, and so on. Each variable is assigned a probability distribution, and the simulation runs thousands or even millions of times, each time drawing random values from these distributions. This approach helps to quantify the uncertainty and variability in the estimates, providing a more nuanced understanding of the potential for alien life. The Drake equation is often criticized for its reliance on assumptions and the lack of empirical data for many of its variables. Monte Carlo simulations address this issue by explicitly incorporating these uncertainties. For instance, the variable representing the fraction of planets that could support life is highly debated. Optimists might argue that life is robust and can emerge under a wide range of conditions, pointing to extremophiles on Earth that thrive in extreme environments. Skeptics, however, might contend that the conditions for life are rare and finely tuned, citing the unique characteristics of Earth. By running simulations with different assumptions, researchers can explore the implications of these varying viewpoints. This method reveals the sensitivity of the equation's outcome to each variable, highlighting which factors have the most significant impact on the estimated number of alien civilizations. One of the key advantages of Monte Carlo simulations is their ability to handle complex, interdependent variables. For example, the probability of life emerging on a planet might depend on factors like the planet's distance from its star, its atmospheric composition, and the presence of liquid water. These factors are not independent. They influence each other in ways that are not always straightforward. Monte Carlo simulations can model these interdependencies, providing a more realistic picture of the potential for life. This approach also allows researchers to test different scenarios. What if the rate of star formation is higher than currently estimated? What if the fraction of stars with planets is lower? By adjusting these parameters, scientists can see how the overall estimate changes, gaining insights into the robustness of their conclusions. Despite their utility, Monte Carlo simulations are not without limitations. The results are only as good as the input data and assumptions. If the underlying distributions for the variables are poorly understood or inaccurately specified, the simulations may produce misleading results. Additionally, the simulations can only explore the range of possibilities based on the given inputs. They cannot predict the likelihood of events that fall outside these parameters. Nevertheless, Monte Carlo simulations remain a valuable tool for exploring the Drake equation, offering a structured way to navigate the vast uncertainties and debates surrounding the search for extraterrestrial life. They provide a framework for integrating diverse viewpoints and testing the sensitivity of the equation to different assumptions, ultimately enhancing our understanding of the cosmos and our place within it. Sensitivity analysis of the Drake equation. The Drake equation, formulated by astronomer Frank Drake, is a probabilistic approach to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. It's a product of 7 variables: the average rate of star formation, the fraction of those stars with planets, the number of planets that could potentially support life, the fraction of those planets where life actually develops, the fraction where intelligent life emerges, the fraction of those civilizations that develop detectable technologies, and the length of time such civilizations release detectable signals. Sensitivity analysis of the Drake equation involves examining how changes in these variables affect the final estimate, highlighting the uncertainties and debates surrounding each factor. Each variable in the Drake equation is subject to considerable uncertainty and debate. For instance, the average rate of star formation is relatively well understood, but the other variables become increasingly speculative. The fraction of stars with planets has been revised upwards due to discoveries of exoplanets, but the number of habitable planets is still uncertain. Estimates for the emergence of life and intelligent life are based on a single data point, Earth, and are therefore highly contentious. Optimists argue that life is likely common, given the sheer number of potentially habitable planets, while skeptics point to the lack of empirical evidence and the potential rarity of the conditions that led to life on Earth. The fraction of civilizations that develop detectable technologies and the length of time they remain detectable are also hotly debated, with pessimists suggesting that civilizations may self-destruct or become undetectable quickly. Sensitivity analysis reveals that the equation is highly sensitive to certain variables. For example, if the fraction of planets where life develops is low, the overall estimate plummets, even if other variables are optimistic. Conversely, if the length of time civilizations remain detectable is long, the estimate increases significantly. This analysis underscores the importance of each variable and the need for more data. It also highlights the philosophical and scientific divides. Some researchers focus on refining the variables based on new astronomical data, while others emphasize the need for a more robust understanding of the emergence and evolution of life. The debate is ongoing, with no clear consensus in sight. The Drake equation serves as a framework for discussion and research rather than a definitive answer. It encourages scientists to think critically about the factors that contribute to the existence of extraterrestrial civilizations. Sensitivity analysis, in particular, helps identify which factors are most critical and where further research could have the greatest impact. It's a reminder that our understanding of the universe is still in its infancy, and there's much more to learn. Whether you're an optimist or a skeptic, the Drake equation and its sensitivity analysis provide a valuable tool for exploring one of humanity's most profound questions: are we alone in the universe? Current estimates and their ranges. The Drake equation, formulated by astronomer Frank Drake, is a probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. It consists of 7 variables, each representing a different factor in the estimation. The equation is often written as n equals r asterisk fp ne fl phi FCL, where N is the number of civilizations with detectable electromagnetic emissions. Let's break down the variables and explore the current estimates and their ranges. The first variable, our asterisk, represents the rate of formation of stars suitable for the development of intelligent life. Current estimates suggest that our galaxy forms stars at a rate of about 1/3 per year. The next variable, FP, is the fraction of those stars that have planetary systems. Thanks to missions like Kepler, we now estimate that nearly every star has at least one planet, with many having multiple planets. The third variable, NE, is the number of planets per solar system with an environment suitable for life. This is where estimates start to diverge significantly. Optimists might point to the abundance of exoplanets in the habitable zone, while skeptics argue that many of these planets may lack the necessary atmospheric or geological conditions. The fourth variable, FL, is the fraction of suitable planets on which life actually appears. This is a contentious point. Some scientists argue that life is ubiquitous given the right conditions, citing extremophiles on Earth that thrive in harsh environments. Others contend that the origin of life may be an extremely rare event, with Earth being a statistical anomaly. The fifth variable, phi, is the fraction of life-bearing planets on which intelligent life emerges. This is perhaps the most debated variable. Some believe that intelligence is a natural outcome of evolution, while others argue that it's a rare fluke. The sixth variable, FC, is the fraction of civilizations that develop a technology that releases detectable signs of their existence into space. This is often assumed to be high, given humanity's own technological trajectory. The final variable, L, is the length of time such civilizations release detectable signals into space. This is highly speculative. Optimists hope that civilizations might exist for hundreds of thousands or even millions of years. Skeptics, however, point to humanity's own trajectory, with concerns about climate change, nuclear war, and artificial intelligence suggesting that advanced civilizations might not last very long. When you plug in the numbers, the estimates for N vary wildly. Optimists might arrive at a number in the thousands, while skeptics might suggest that N is 0. The truth likely lies somewhere in between, but without more data, it's impossible to say for sure. The Fermi Paradox and the Drake Equation. The Fermi Paradox and the Drake Equation are two interconnected concepts that have sparked intense debate and speculation among scientists and enthusiasts alike. The Fermi Paradox, named after physicist Enrico Fermi, questions why, given the high probability of the existence of extraterrestrial civilizations, we have yet to find any concrete evidence of them. The Drake Equation, formulated by astronomer Frank Drake, attempts to estimate the number of communicative extraterrestrial civilizations in the Milky Way. It's a probabilistic argument that considers factors like the rate of star formation, the number of planets that could potentially support life, and the likelihood of life emerging on those planets. The Drake Equation is composed of several variables, each representing a different factor in the estimation of extraterrestrial civilizations. These variables include the average rate of star formation, the fraction of those stars that have planets, the number of planets that could potentially support life, the fraction of those planets where life actually develops, the fraction of those planets where intelligent life emerges, the fraction of those civilizations that develop detectable technology, and the length of time such civilizations release detectable signals into space. Each of these variables is a subject of ongoing research and debate. For instance, the fraction of stars with planets has been significantly updated thanks to missions like NASA's Kepler, which has discovered thousands of exoplanets. However, other variables, like the likelihood of life developing on a habitable planet, remain highly speculative. Assumptions and debates surround each variable in the Drake Equation. Optimists argue that life is likely to be common, given the sheer number of potentially habitable planets. They point to the rapid emergence of life on Earth soon after the planet became habitable. Skeptics, however, argue that the emergence of intelligent life might be an extremely rare event. They highlight the numerous coincidences and evolutionary steps that led to human intelligence, suggesting that such a sequence might be highly improbable. The debate is further complicated by the fact that we only have one example of life on Earth, to base our assumptions on. This lack of data makes it challenging to accurately estimate the probabilities involved in the Drake equation. The Fermi Paradox adds another layer of complexity to these debates. If the Drake equation suggests that there should be many communicative extraterrestrial civilizations, why haven't we detected any? This paradox has led to various hypotheses, ranging from the zoo hypothesis, which suggests that extraterrestrial civilizations are deliberately avoiding contact with us, to the Great Filter hypothesis, which posits that there is some barrier that prevents civilizations from reaching a detectable stage. Some scientists argue that the paradox might be resolved by the fact that the average lifespan of a communicative civilization is relatively short, making it unlikely for us to overlap with another civilization's communicative phase. Others suggest that we might simply not have the right technology or methods to detect their signals. The interplay between the Fermi paradox and the Drake equation continues to fuel scientific research and public imagination, driving our quest to understand our place in the universe. Alternative approaches to estimating alien life. The Drake equation, a probabilistic argument estimating the number of active, communicative extraterrestrial civilizations in the Milky Way, has been both celebrated and critiqued since its inception. It considers factors like the average rate of star formation, the fraction of stars with planets, and the number of planets per star that could support life. However, the equation's reliance on uncertain variables has led to alternative approaches that attempt to estimate the likelihood of alien life more indirectly. One such approach is the rare Earth hypothesis, which posits that the emergence of intelligent life on Earth may be an exceedingly rare or even unique event in the universe. Proponents of this view argue that Earth's unique combination of a large moon, plate tectonics, a strong magnetic field, and a large gas giant like Jupiter in the outer solar system may be highly unusual. They point to the lack of definitive evidence for extraterrestrial life despite decades of searching as supporting evidence. This perspective is often seen as pessimistic, as it suggests that the conditions for intelligent life are so specific that they may not exist elsewhere. On the other end of the spectrum are approaches that consider the sheer scale of the universe and the high probability of life emerging given the right conditions. Some scientists argue that even if the probability of life on any given planet is low, the vast number of potentially habitable planets in the universe makes the existence of extraterrestrial life highly likely. This view is often referred to as the principle of mediocrity, which suggests that Earth and its life forms are not exceptional in any way. Advocates of this perspective point to the rapid discovery of exoplanets and the growing evidence of extreme life forms on Earth that can survive in harsh environments as reasons to be optimistic. Another alternative approach involves looking for biosignatures, or signs of life, in the atmospheres of exoplanets. By analyzing the light that passes through a planet's atmosphere, scientists can detect the presence of certain gases that might indicate biological activity. For example, the presence of oxygen and methane together could suggest the existence of life, as these gases are often produced by living organisms. This method is still in its early stages, but it holds promise for directly detecting signs of life on other planets. The debate between these different approaches continues, with each offering unique insights and challenges in the ongoing search for extraterrestrial life. The role of astrobiology. Astrobiology, the interdisciplinary field that studies the origin, evolution, distribution, and future of life in the universe, plays a pivotal role in interpreting and refining the Drake equation. This equation, formulated by astronomer Frank Drake, aims to estimate the number of communicative extraterrestrial civilizations in the Milky Way. At its core, the Drake equation is a probabilistic argument that considers factors like the average rate of star formation, the fraction of stars with planets, and the number of those planets that could potentially support life. Astrobiology provides the scientific foundation for many of these variables, drawing from biology, chemistry, planetary science, and astronomy to inform our understanding of where and how life might arise. One of the key variables in the Drake equation is the fraction of planets that could potentially support life, often referred to as the habitable zone. Astrobiologists study the conditions necessary for life as we know it, such as the presence of liquid water, a stable atmosphere, and a suitable energy source. For instance, the discovery of extremophiles on Earth, organisms that thrive in extreme environments like deep-sea vents or acidic hot springs, has expanded our understanding of where life might exist. This knowledge directly impacts the Drake equation by suggesting that life could potentially exist in a broader range of environments than previously thought. However, debates persist about the exact parameters of habitability, with some scientists arguing for a more conservative view based on Earth-like conditions, while others advocate for a more inclusive definition that encompasses a wider array of potential habitats. Another crucial variable is the fraction of habitable planets where life actually develops. Astrobiology explores the chemical and physical processes that lead to the origin of life, such as the formation of complex organic molecules and the assembly of cellular structures. The study of prebiotic chemistry, for example, investigates how simple molecules might have combined to form the building blocks of life. While significant progress has been made in understanding these processes, the exact pathways and probabilities remain uncertain. Optimistic views suggest that life might be a relatively common outcome given the right conditions, while skeptical perspectives emphasize the numerous steps and unlikely events that must occur for life to emerge. This debate is central to the Drake equation, as it directly influences the estimated number of life-bearing planets in the galaxy. The Drake equation also considers the fraction of life-bearing planets where intelligent life evolves. Astrobiology examines the evolutionary pathways that lead to intelligence, drawing from studies of Earth's biodiversity and the factors that contributed to the rise of human-like cognition. The fossil record and comparative studies of animal behavior provide insights into the conditions that might favor the development of intelligence. However, the rarity of intelligent life on Earth, with only one known instance, makes it difficult to generalize. Some scientists argue that intelligence is a rare and contingent outcome of evolution, while others suggest that it might be a more common feature of complex life forms. This uncertainty is reflected in the wide range of estimates for this variable in the Drake equation, highlighting the need for further research and exploration. The impact of technological advancements. Technological advancements have significantly influenced our ability to explore and understand the cosmos, directly impacting the variables of the Drake equation. This equation, formulated by astronomer Frank Drake, estimates the number of communicative extraterrestrial civilizations in the Milky Way. One of the most affected variables is the likelihood of life developing on habitable planets, NL. Advances in astrobiology and the study of extremophiles on Earth have expanded our understanding of where and how life can emerge. For instance, the discovery of life in extreme environments, such as deep-sea vents and acidic lakes, suggests that life might be more resilient and adaptable than previously thought. This optimism is fueled by technologies like the James Webb Space Telescope, which can analyze the atmospheres of exoplanets for biosignatures, potentially increasing the value of NL. However, technological progress also introduces skepticism. The variable for the fraction of civilizations that develop detectable technology, FC, is hotly debated. Some argue that technological advancement might be rare due to self-destruction or environmental collapse. The Fermi Paradox, which questions the absence of observable extraterrestrial intelligence despite high probability estimates, fuels this skepticism. Proponents of this view point to humanity's own struggles with climate change and nuclear threats as evidence that advanced civilizations might not last long enough to be detected. This perspective suggests that FC could be quite low, despite our own technological achievements. Moreover, the rate at which civilizations release detectable signals, L, is another contentious variable. The advent of digital communication and the shift from analog signals like radio broadcasts to encrypted digital data have made it harder to detect extraterrestrial signals. Some optimistic scientists believe that advanced civilizations might use more sophisticated communication methods, like laser pulses or neutrino beams, which we might not yet be able to detect. On the other hand, skeptics argue that the window for detecting signals might be narrow, as civilizations could quickly evolve beyond detectable technologies. This debate highlights the uncertainty in estimating L, despite our technological advancements. In summary, technological advancements have both broadened and narrowed our estimates of the variables in the Drake equation. While they have expanded our understanding of where life might exist and how it might survive, They have also introduced complexities and uncertainties about the detectability and longevity of extraterrestrial civilizations. This dual impact underscores the need for continued exploration and innovation in our search for extraterrestrial life. The search for extraterrestrial intelligence, SETI. The Drake equation, formulated by astronomer Frank Drake, is a probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. It's a product of several variables, each representing a different aspect of the likelihood of life emerging and evolving to the point of developing detectable technology. The equation is often used in discussions about the search for extraterrestrial intelligence, SETI, which is a collective term for scientific searches for intelligent extraterrestrial life. The equation is typically written as n equals r asterisk Fp, Ne, Fl, Phi, Fc, L, where n represents the number of civilizations in the Milky Way galaxy whose electromagnetic emissions are detectable. R asterisk is the average rate of star formation per year in our galaxy. Fp is the fraction of those stars that have planetary systems. N is the number of planets per solar system with an environment suitable for life. Fl is the fraction of suitable planets on which life actually appears. Phi is the fraction of life-bearing planets on which intelligent life emerges. Fc is the fraction of civilizations that develop a technology that releases detectable signs of their existence into space. L is the length of time such civilizations release detectable signals into space. Each of these variables is a topic of ongoing debate and research. For instance, our asterisk is relatively well understood due to ongoing astronomical observations, but Fp and Ne are less certain. The discovery of exoplanets has provided some data, but the habitability of these planets is still largely theoretical. Fl, Phi, and Fc are even more speculative, as they depend on our understanding of abiogenesis, evolution, and the development of technology, all of which are complex and not fully understood processes. L is also uncertain, as it depends on the longevity of civilizations and their willingness or ability to communicate. Optimists might point to the rapid development of technology on Earth as evidence that life could quickly become intelligent and technologically advanced. Skeptics, however, might argue that the numerous challenges life has faced on Earth suggest that the emergence of intelligent life is an extremely rare and unlikely event. The assumptions behind the Drake equation are a significant point of contention. Critics argue that the equation makes too many assumptions based on incomplete or anecdotal evidence. For example, it assumes that the emergence of life on Earth is a typical case, which may not be true. It also assumes that intelligent life will inevitably develop technology and attempt to communicate, which may not be the case. Despite these criticisms, the Drake equation remains a valuable tool for stimulating scientific discussion and research. It provides a framework for thinking about the factors that might influence the existence of extraterrestrial civilizations. SETI uses this framework to guide its searches, focusing on stars and planets that are most likely to harbor life based on our current understanding. The organization employs various methods, including radio telescopes and optical telescopes, to search for signals or other evidence of intelligent life. The search is ongoing, and while no definitive evidence has been found yet, the potential implications of such a discovery make it a compelling and worthwhile endeavor. The Drake equation and the Great Filter Hypothesis. The Drake equation, formulated by astronomer Frank Drake, is a probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. It considers factors like the average rate of star formation, the fraction of those stars with planets, and the number of those planets that could potentially support life. The equation is often written as n equals r asterisk Fp, Ne, Fl, Phi, Fc, L, where n represents the number of civilizations with detectable electromagnetic emissions. Each variable stands for a different aspect of the likelihood of life emerging and evolving to a communicative stage. The Great Filter Hypothesis, on the other hand, is a theoretical model that suggests there's some barrier that makes the evolution of life extremely difficult or unlikely. This filter could be behind us, meaning life is incredibly rare, or it could be ahead of us, implying that civilizations like ours don't last long. The hypothesis is often discussed in relation to the Fermi Paradox, which questions why, given the high probability of the existence of extraterrestrial civilizations, we haven't found any concrete evidence of them yet. Debates surrounding the Drake equation often revolve around the assumptions made for each variable. For instance, the fraction of planets that could support life, FL, is highly debated. Optimists might point to the discovery of extremophiles on Earth, organisms that thrive in extreme environments, suggesting life could emerge in a wide range of conditions. Skeptics, however, argue that Earth's conditions are exceptionally hospitable, making complex life a rarity. Similarly, the number of civilizations that develop detectable technology, FC, is contentious. Some argue that technological advancement is an inevitable part of evolution, while others believe it's a fluke of Earth's specific circumstances. The Great Filter hypothesis introduces a grim perspective. If the filter is behind us, it implies that life is extraordinarily rare, and we're among the lucky few. This could mean that the emergence of life from non-life, abiogenesis, is incredibly difficult, or that the transition from single-celled to multi-celled organisms is a significant hurdle. If the filter is ahead of us, it suggests that civilizations like ours don't survive for long. This could be due to self-destruction, such as nuclear war or climate change, or external factors like asteroid impacts or gamma-ray bursts. The hypothesis is a stark reminder of the precariousness of our existence and the importance of addressing global challenges, criticisms, and controversies. The Drake equation, formulated by astronomer Frank Drake, is a probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. It's a product of 7 variables: the average rate of star formation, the fraction of those stars that have planets, the number of planets that could potentially support life, the fraction of planets that actually develop life, the fraction of life-bearing planets that develop intelligent life, the fraction of intelligent civilizations that develop detectable technologies, and the length of time such civilizations release detectable signals into space. Each of these variables is a topic of debate, with optimistic and skeptical views shaping the discourse. Critics often point out that the Drake equation is filled with unknowns. The equation's first few terms, dealing with star formation and planet development, are relatively well understood thanks to modern astronomy. However, the latter terms, particularly those dealing with the emergence of life and intelligence, are highly speculative. Skeptics argue that without empirical data, these terms are little more than guesses. For instance, the fraction of life-bearing planets that develop intelligent life is hotly debated. On Earth, life emerged relatively quickly, but intelligence took billions of years. Some argue that intelligence is a rare fluke, while others believe it's an inevitable outcome of evolution. Assumptions about the prevalence of life and intelligence are central to the controversy. Optimists, like Drake himself, often cite the principle of mediocrity, which suggests that Earth is a typical planet and that life and intelligence are likely common. They point to the rapid emergence of life on Earth and the discovery of extremophiles, organisms that thrive in extreme environments, as evidence that life might be robust and adaptable. On the other hand, skeptics argue that Earth might be a rare gem, with a unique combination of factors that allowed life to emerge and intelligence to evolve. They highlight the lack of definitive evidence for extraterrestrial life despite decades of searching. Another contentious point is the L factor, the length of time civilizations release detectable signals. Optimists hope that advanced civilizations might have long lifespans, while skeptics worry that civilizations might self-destruct or become undetectable. This debate is influenced by our own civilization's trajectory and the potential consequences of technological advancement. Additionally, the equation assumes that intelligent life would develop detectable technologies, an assumption that might not hold true for all potential civilizations. Some critics argue that the equation is anthropocentric, based too much on our own experiences and expectations. Despite these criticisms, the Drake equation remains a valuable tool for stimulating discussion and guiding research in the search for extraterrestrial intelligence. Recent updates and revisions. The Drake equation, formulated by astronomer Frank Drake in the 1960s, has long been a tool for estimating the number of communicative, intelligent civilizations in our galaxy. It considers factors like the average rate of star formation, the fraction of stars with planets, and the likelihood of life developing on those planets. Recently, updates and revisions to this equation have been proposed, reflecting new scientific discoveries and refined understanding. One of the most significant updates involves the variable representing the fraction of planets that could potentially support life. Initially, this was a speculative guess. However, data from missions like NASA's Kepler and the ongoing work of the Transiting Exoplanet Survey Satellite, TESS, have provided a more accurate picture. These missions have identified numerous exoplanets within the habitable zones of their stars, where liquid water could exist. This has led to a more optimistic revision of this variable, as the number of potentially habitable planets is now known to be much higher than previously thought. Debates continue about other variables, such as the fraction of these planets where life actually develops. Some scientists argue that the building blocks of life, like amino acids, are common in the universe, pointing to optimistic estimates. Others remain skeptical, citing the rarity of complex life on Earth and the lack of definitive evidence for life elsewhere. The discovery of extremophiles, organisms thriving in extreme environments on Earth, has also influenced these discussions. This has led to a broader definition of habitable zones, considering not just water but also other conditions that could support life. The Drake equation also considers the likelihood of intelligent life developing and the fraction of civilizations that develop detectable technologies. Here, opinions diverge widely. Optimists point to the rapid technological advancement on Earth as a model for what could happen elsewhere. Skeptics, however, highlight the numerous evolutionary dead ends and the rarity of intelligent life on our own planet. The Fermi Paradox, contrasting the high probability of extraterrestrial civilizations with the lack of contact, fuels these debates. Recent updates to the equation have incorporated these discussions, reflecting a more nuanced understanding of the challenges in detecting intelligent life. Implications for future research. The Drake equation, formulated by astronomer Frank Drake, is a probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. It considers factors like the average rate of star formation, the fraction of those stars with planetary systems, and the number of planets that could potentially support life. The equation also takes into account the fraction of planets where life actually develops, the fraction of those where intelligent life emerges, and the likelihood that such civilizations develop detectable technologies. Lastly, it considers the length of time such civilizations release detectable signals into space. Each of these variables is a topic of ongoing debate and research. One of the most contentious variables is the fraction of planets where life actually develops, often denoted as FL. This is where assumptions and debates intensify. Optimists argue that life is likely to be robust and adaptable, pointing to extremophiles on Earth that thrive in extreme environments. They suggest that if life can arise in such harsh conditions, it might be common elsewhere. Skeptics, however, highlight the unique conditions of Earth, such as its magnetic field, plate tectonics, and the presence of a large moon, which have all contributed to its habitability. They argue that these factors might be rare, making the emergence of life less likely. Another hotly debated variable is the fraction of planets where intelligent life emerges, often denoted as phi. Optimists contend that evolution tends to favor increased complexity and intelligence, as seen on Earth. They speculate that if given enough time, intelligent life could emerge on any planet with life. Skeptics, however, point out that intelligence is not necessarily an inevitable outcome of evolution. They argue that intelligence might be a rare fluke, or that it might not always lead to technological civilizations. For instance, dolphins are intelligent but have not developed technology. Moreover, the timeline for the emergence of intelligence is also debated. On Earth, it took billions of years for intelligent life to evolve, a timescale that might not be common elsewhere. The implications for future research are profound. The Drake equation serves as a roadmap for astrobiology, guiding scientists in their search for extraterrestrial life. It underscores the need for interdisciplinary research, combining astronomy, biology, geology, and other fields. For instance, the study of exoplanets can provide data on the number of stars with planetary systems and the number of planets in the habitable zone. The search for biosignatures, like methane or oxygen, in exoplanet atmospheres can help estimate the fraction of planets where life develops. Meanwhile, studies of extremophiles on Earth can broaden our understanding of the conditions under which life can arise and persist. The Drake equation also highlights the importance of understanding the evolution of intelligence and technology. By studying the evolution of intelligence on Earth and exploring the factors that contributed to the development of human technology, scientists can better estimate the likelihood of intelligent life elsewhere. Ultimately, the Drake equation is not just a tool for estimating the number of extraterrestrial civilizations. It's a catalyst for exploration and discovery. As we wrap up our journey through the cosmos with the Drake equation, let's recap the key points that have guided our exploration. We've broken down each variable, from the rate of star formation to the fraction of planets that could harbor life, and even the longevity of civilizations willing and able to communicate. We've seen how assumptions and debates shape our understanding, with optimists painting a picture of a galaxy teeming with life, and skeptics urging caution, reminding us that life as we know it might be a rare, precious anomaly. The Drake equation isn't just a mathematical puzzle. It's a mirror reflecting our hopes, fears, and curiosity about our place in the universe. It's a tool that brings us together, sparking conversations and collaborations across disciplines, from astronomy to biology, from philosophy to engineering. So what's next? The search for extraterrestrial life is far from over. With each new discovery, each new mission to Mars or Europa or the distant exoplanets, we're inching closer to answering one of humanity's oldest questions. Are we alone? We'd love to hear your thoughts. What do you think the Drake equation tells us about the likelihood of alien life? Share your views in the comments, and let's keep the conversation going. And stay tuned, because our journey through the cosmos is just beginning. In our next video, we'll be diving into the fascinating world of exoplanets and the cutting-edge technology that's helping us explore them. Until then, keep looking up, keep wondering, and keep exploring. The universe is waiting.